So in this part of the video, we're going to do examples 7 and 8, and we're going to talk about the trapezoidal rule. As we have been seeing throughout this topic, there are several ways of approximating an integration using geometric shapes. Trapezoid is another popular shape, and right over here we have the trapezoid formula, just of a trapezoid you learned in geometry. It's base sub 1 plus base sub 2 divided by 2 times the height. There is a rule officially, and this basically you can see as it's basically saying you take the endpoints of your interval and subtract them, and then you do 2 divided by the number of subintervals you have, and then you basically put all of your heights in here. I think that's way too much to remember, and there's times when that doesn't work for us because our distances in between are not equal. So we're going to go ahead and just use however many trapezoids that we need to. We might do some fancy factoring here in a few minutes. So we're supposed to use trapezoidal rule for the function sine x for trapezoids. So I'm going to set up for 4 trapezoids. All right, I know that I divide by 2 on all of them. Notice I'm leaving a little gap of space this time. And then I set up for base times height. I'm going to have to write tinier than that to get this in there. So I'm setting up for my base times my 2 bases in there. Okay. One thing you should notice is that the height in between, or the height of remember our trapezoid is laying on its side, right? So the height of the trapezoid is in here. And in this particular example, the heights are consistent. So my heights are all pi over 4. So I'm going to put that in there on all of them. Then I'm going to have to evaluate the function at each one of these x values. I'm going to erase that because I made a mess of that. So each one of these x values I have to evaluate the height at. So I'm going to have sine of 0. And then I'm going to have sine of pi over 4. And then I'm going to repeat this height on the next trapezoid. So this one gets repeated. So I get sine of pi over 4 times sine of pi over 2. And then I'm going to go to the next trapezoid, and I'm going to repeat this height. So sine of pi over 2, and then I'm going to go to this height here, and sine of 3 pi over 4. And then I'm going to repeat this height, so sine of 3 pi over 4 times sine of my final height, which would be pi. Okay, so now we're going to do our calculation. But notice that this is in every single one of them. So I'm going to use some fancy algebra. I'm going to factor that out. So when I factor that out, I get pi over 4 times 2 in the denominator, which would really be pi over 8. So that has been factored out. Now I'm going to do my sine calculations, getting out my good old unit circle. I know I am out 1, up 0. I got a lot of over 4s. I know the y coordinated over 4 is square root of 2 over 2. I know this is out 0, up 1. Again, at pi over 4, my y coordinate is square root of 2 over 2. And then out -1, up 0. So sine of 0 is 0. Sine of pi over 4, square root of 2 over 2. Sine of pi over 4 again, square root of 2 over 2. Sine of pi is 1. Sine of pi again is 1. Sine of 3 pi over 4, square root of 2 over 2. Again, sine of 3 pi over 4 is square root of 2 over 2, and then sine of pi is 0. So you'll notice that the parentheses really don't matter. I could just add these up. So I've got 1 pi over 2, 2 pi over 2, 3 pi over 2, 4 pi's over 2. So not pi's over 2, square roots of 2 over 2. And then it looks like I have left a 1 plus a 1, which is 2. We don't have to simplify, really. I'm going to, just to get us, because I don't know what delta math is probably going to simplify your answer. So 2 goes into 4 twice. I noticed that I have a greatest common factor of 2, so I could pull that out. So I see 2 times pi over 8, and then what would be left here would be a square root of 2 plus 1. So this could simplify a bit. So our most simplified answer is pi over 4, and they may rearrange this, they might not. 1 plus square root of 2. All right, finally, we're back to a tabular stem. We're going to use this to do the speed in miles per hour of a cyclist at various times. So we're going to use a trapezoidal approximation with 6 subintervals to find the distance in miles of the cyclist traveled in 12-minute time interval. Okay. So I am going to set up for 6 trapezoids. 2, 3, 4, 5. Okay. And I'm going to use my more traditional divide everything by 2. And then I'm setting up the heights. So when we are in a tabular stem like this, our heights actually come from the distance in between. So my first height is 2. My next height is 3. My next height is 1. My next height is 3. My next height is 1. And my next height is 2. Okay. Then we're going to use our actual heights here as the bases. So this is the first base would be 33. And then the next one would be 25. And then I'm going to repeat so the 25 was in both. Now I'm going to repeat the 25. So 25 plus 27. Then I'm going to repeat the 27. 27 plus 13. Then I'm going to repeat the 13. So 13 plus 21. Then I am going to, let's find something different. I'm running out of colors. 21's repeated times 5. Okay. Then we're going to repeat the 5. And then I'm going to use 9. Okay. So some things that I notice that every single one of them has a divide by 2. So rather than messing with fractions, I'm going to go ahead and factor that out. It's really the only thing they have in common. So I'm going to go ahead and pull that out. I'm going to start doing some adding here. So I know that I've got 58 times 2 plus 52 times 3 plus 40 times 1 plus 34 times 3 plus 26 times 1 plus 14 times 2. And then again, I'm going to keep the multiply by 1/2 out front. When I start multiplying those together, I get 116 plus 156 plus 40 plus 102 plus 26 plus 28. And then finally, I end up with 1/2 times 468. And then when I divide that by 2, I get 234. Okay. And then we know it was because it was a speed of miles per hour a cyclist has at various times. So we know that this would be multiplied, this would be miles, is what we would be measuring. Wait a minute. Let's see what it said. Find the distance in miles. Okay, that's not the miles, is it? Okay. that's the miles per hour times, we need to deal with, these were minutes, so we need to, oh, I erased and I shouldn't have, sorry. We need to deal with the fact that this was 12-minute time interval, but we need to figure it out, that we need to figure out the distance in miles, okay? So this was in miles per hour times the minutes. This is in miles per hour times minutes. Okay, so we need to do some conversion here. So we know we've got 234 miles per 1 hour. We're going to multiply that by, we know 1 hour is divided into 60 minutes. So we know that and then we're going to multiply that times the minutes, which was right here, okay? So we know the hours cancel, the minutes cancel. So I'm basically taking 234 and dividing by 60, which would get me 3.9 miles total. Okay, I think that's it. And then there's just a little exam tip here. On the AP exam, it's very important that you show the sum of products. However, you are constructing an approximation of area, either using the Riemann sums or a trapezoidal sum. In other words, don't perform any arithmetic calculation in your first step. The readers want to see the structure of your approximation method. So basically, you need to show that structure and then maybe do a calculation, okay?